Look at the operating budget of a standard heavy manufacturing plant. Hydraulic fluid represents under 2% of expenses. Operations executives ignore it entirely. Yet that exact fluid is the failure point for 70% of heavy equipment breakdowns. The factory floor grinds to a halt because the fluid chemistry is compromised. This image shows the physical consequence of that neglect. Thick, white polymer builds up and leaks directly out of the nozzle junction on an injection molding machine barrel. The metal shows clear thermal discoloration. You're running a multi-million-dollar asset on degraded oil. It is the engineering equivalent of buying a high-performance supercar and filling the engine with used cooking oil. The system will inevitably seize. To diagnose this systemic degradation, we have to isolate the variables. Polymer leakage traces back to two distinct pairs of failure. Human error interacts with machine wear, and process methods conflict with the operating environment. This chart shows the interaction between these variables. Notice the human factors. An operator lacking the experience to calibrate temperature accelerates machine wear and deteriorates the nozzle seals. A failure of this complexity requires mapping the root cause. Over the last decade, equipment manufacturers prioritized a smaller physical footprint. They reduced the size of hydraulic fluid reservoirs by up to 40%. Smaller tanks give the oil less time to cool. The fluid absorbs an immense thermal load. It degrades into a sticky, sub-micron oxidative deposit called varnish. These particles bypass standard mechanical filtration. This chart graphs the relationship between injection pressure and polymer leakage. At 140 megapascals, the leak rate is 18 milliliters per hour. It surges past 60 milliliters per hour as pressure reaches 150 megapascals, breaking down the system's containment boundary. Standard maintenance protocols miss this threat. At high operating temperatures, varnish remains entirely soluble in the oil. It hides in plain sight. The damage occurs when that fluid circulates away from the heat source. The varnish precipitates out as the oil hits cooler areas, like servo valves. It coats the internal mechanics with a hard residue. This is a metal mold cavity contaminated by that process. You can see the dark, oily residue pooling across the precision surfaces.
Degraded oil acts as a physical abrasive. It increases mechanical friction and unpredictably seizes valves. Electrostatic oil cleaning attacks the root cause. We apply controlled, high-voltage electrostatic charges directly to the fluid. This physically attracts and strips the sub-micron varnish out of the oil. Agile maintenance teams deploy a mobile kidney loop filtration system. They plug directly into the machine while it continues to mold parts at full capacity. By purifying the oil to a state cleaner than virgin stock, you extend the service life of the hydraulic fluid to 100,000 hours. Total new oil consumption drops by 95%. This is the baseline capability restored. A clean, repaired metal mold insert sits free of oxidative residue. It is ready to hold tight tolerances without friction. A flat monthly fluid reliability retainer entirely replaces the unpredictable costs of scrapped materials. It prevents ruined servo valves. The health of the physical hardware is entirely dependent on the chemistry of the fluid inside it. Fluid integrity dictates machine integrity. Restorative engineering proves that hardware replacement is a waste of capital. We fix the operating environment. Equipment manufacturers will continue building smaller, hotter machines. By isolating and managing this microscopic threat, you secure the operational margins of the entire factory floor.